Okay, people, so I am back. So this is how we do the I/O without using any interrupts or the DMA chip, fully programmed, fully using busy waiting. If we use the interrupts, we are going to see the program that we need to write. So this program will take CPU time. If every character takes 10 milliseconds to print, which is fast for a printer, but very slow for a CPU. Okay, so I have to spend 10 milliseconds around here, waste that time I will wait for the printer to be ready. So why don't I use interrupts instead of waiting here? Just block this process, context switch, do something else, and come back. Context switching takes some time, but it is not longer than 10 milliseconds. Okay, 10 milliseconds is a very long time. So that's what we are going to do. Okay, so enough time for a context switch and do some useful work. So solution is to use interrupts, and this is what happens. So I have two parts now. When somebody say that print this buffer for me, first I copy it from the buffer, user buffer to the kernel buffer. I enable the interrupts. Okay, I wait until the printer is ready for the first time. Okay, and I put the first character into the special register, and then I block myself. I call the scheduler. Schedule somebody else so that they can use the CPU. So this is the initial part of printing. And then when the interrupt happens, when the printer says that, okay, I'm ready. When the printer says that, okay, I'm ready, this part runs. This is the interrupt handling, part of the interrupt handling routine. Okay. It says that if the count is 0, then I have to go back and unblock the user because everything is done. If counter is not 0, then put this PI into this location, decrement the count by 1, increment I by 1, and I acknowledge the interrupt saying that, okay, interrupt controller, I handled your interrupt. Okay, now you can free to cause another interrupt. This interrupt is done, and I return from the interrupt. Okay, every time printer says that I am ready to print a new character, this will run. And the original process, which runs this one, okay, will be kept blocked until everything is printed one by one in this case. So every time a character is printed, a context switch has to happen. And context switch, as you know, takes time. But it says that, the book says that it won't take more than 10 milliseconds to do a context switch, and after that doing some useful things. Okay, so this is interrupt-driven I/O. It has two parts. This is the interrupt part. This is the initial part where we started the input-output. Okay. This is T, and this is what you are missing. Suleiman and ChatGPT, we are all having our T's here. Okay. Good. Any questions? We continue then. So the obvious advantages, okay. It saves lots of CPU time. The obvious disadvantages, I have to do the context switching, interrupt-driven I/O. Interrupts take some time. Okay, so this is not 100% efficient. That's what I would say. This is not 100% efficient. I mean, remember the time that I wasted here? I saved some part of it. I saved some wasted time in this busy loop, but some saved time will be wasted in context switching. So the solution is to use the DMA. I'm going to do almost the same thing here. Start the I/O process, but for this one I will not do it because a DMA chip will handle the printing the characters one by one. Okay, so I'm going to use the DMA chip. So for the DMA, of course, I need the DMA controller, DMA chip. That's the obvious disadvantage. I need it, DMA chip. That complicates my computer system a little bit, but it's most of the time it's worth it. Okay, so the DMA controller is smart enough to run this loop, okay, between the main memory and the printers controllers. So it's going to move these characters to the printer's data register one by one. It is smart enough to do that. Okay. So in essence, okay, in a way that DMA is actually a programmed I/O. The only thing is, okay, this is done by the DMA chip, not by the CPU. You are saying that I have a very low grade CPU, okay, very simple CPU. All it does is move data around between the main memory and the I/O controller devices. Okay, and I am programming this CPU, this new CPU, which I call the DMA controller, to do these simple tasks. So they are not doing interrupts. It is not doing anything fancy. All it does is copying data from memory to the printer buffer. Okay, and it doesn't cause interrupts. It doesn't keep my CPU busy, and this is what it does. Okay, so initially I copy from the user space to the kernel space. I set up my DMA controller saying that this data will be moved from this location to the printer, and I block myself. And this is what interrupt service procedure does. Okay, when the DMA chip says that I did all of your transfer, okay, I did all of your transfer. Now you can unblock your user, and I just unblocked my user. So the interrupt will happen only once. The CPU will be interrupted only once, and in that case, I will unblock myself. So this is very, very efficient. Doesn't cause any context switch other than the initial ones, and it doesn't keep my CPU busy. Of course, the downside is I have to have this DMA chip available on my system. Okay, any questions? Okay, go to my favorite. Write 32 code to set up DMA chip to print a buffer of ASCII characters to the printer controller. I know what's happening. I am hitting the enter button. That's what it's okay. I didn't complete it. Let me stop generating it. Okay. Enter. Now I do it. Save and submit. Second time I submitted it did slow because it thinks that I am abusing the system. So just to show you, I don't know what kind of answer I am going to get, but just to show you how simple this DMA in terms of CPU time, of course. Okay. Well, it's going to take some time, maybe. A combination of code and hardware-specific configurations, yes. Here's an example. Slow. Initialize the DMA controller. Okay, somebody tell me what this. Okay, come on, just read them. Okay, so DMA register port is this one. Okay, initialize the DMA channel to 2. Obviously, you need to specify some channels. Okay, so this is the address for the DMA command. So DX I moved it, and this is the command for initializing it. And just I moved 04 to this address. So I initialize the DMA controller. Okay, so am I using IO port space or the memory mapped IO in this case? Question for you. Am I using IO port space or the memory mapped IO?
IO port.
Why do you say that?
Because you give directly the address of.
So I am how are you are saying this right? Exactly, yeah. Because you are saying that I am using this out instructions, okay? So this is it's already said that, okay? So this one is DMA mode register port, single mode auto initialize, etc. So I am page register port. These are the details of how the things are done with the, okay? Am I done? Oh, network error. I think it was too slow and didn't want to keep it. So basically what you do is you put special numbers into special registers, you initialize your DMA register, and I didn't get to see the loop that actually I didn't yeah, well, I was going to see the loop, but I didn't get to see how I started the data copying on the DMA chip, but basically that's the idea. So I am using the IO port spaces. Low count register. See this one? Number of characters to transfer. It looks like I have 13 characters register. And what is this? Transfer count high register port. Less than, okay, so it is 0, I guess. Anyways, so do this experiment yourself. Try to understand how the things how the DMA is programmed. Okay, good. And if we move in our discussion of IO software principles, this is what we are going to see. This is the structure of our operating system. At the bottom, we have our hardware. Our interrupt handlers is right above the hardware. They are the lowest level operating system components, interrupt handlers. When the interrupt happens with the printer or the keyboard or the desk, okay, these interrupt handlers will be called by the help of the interrupt controllers. Remember, the interrupt controller says that this device has caused the interrupt, and I am going to choose this interrupt handler to handle this interrupt. Okay, on top of them are the device drivers. Device drivers know how to communicate with the devices themselves. For example, this one would have been a part of the device driver for the printer, maybe. Okay. For the printer, maybe this would have been a device driver, or this one, if I am using the polling, would have been the part of the printer device driver. This one knows how to print a buffer to the printer using busy waiting. Okay, so on top of the interrupt handlers, I have the device driver, and on top of it, I have device independent operating system software. This one just calls the device driver functions, for example, to printing some bytes, some characters to a dot matrix printer is very different than printing some characters on a laser printer. Okay, their technologies are so different. One is purely mechanical, okay. The other one is mechanical plus lots of electronics, right? But for me, all I do is I just send a file to the printer. That's it. So that part is the device independent operating system software. And on top of it, I have the user level IO software, which is for the end user, which uses only the system calls. Okay. And let's see again, go back to this interrupt handlers. Let's see. We did this actually before. We did this before. This is just a reminder, just to repeat it. And maybe we can understand more details even better here. So typical steps after hardware interrupt completes. Okay. When the hardware interrupt completes, when the interrupt occurs, it's saying that, okay, there is an interrupt. So as soon as the interrupt happens, the hardware, okay, saves all the registers, required registers. But if I didn't save any registers, not by the hardware, I save them, okay, and I set up a context. Context means that my stack, call stack and data stack and etc. Make it available for my new context. I'm preparing for the context switch. Okay, I set up the stack for the interrupt service procedure, and I tell the interrupt controller that I got the interrupt now. I am handling it. Okay, I am handling it. So it is the task of the interrupt controller to enable the interrupts again, or continue keeping them disabled if I have an interrupt controller. Okay, then copy register from save to process table. I am saving all of my registers. Okay, after I am handling the interrupt, after I am running the interrupt service procedure, okay, I do all of these in the other way, the reverse way, copy everything back and etc. And I do the scheduling. Okay, choose which interrupt to run next, and I program the MMU context for the next process. So I invalidate all the cache. I invalidate all the look aside buffer. Okay. MMU, setting up the MMU is very setting up the MMU and etc. And then I load everything. I load everything, including the PSW from the save data and continue. Okay, so this what happens when I return, when I start the interrupt and when I return from the interrupt. Okay, so this is in a way how we understand why this interrupt handling is expensive, because I set up context. Setting up the context means that invalidating your cache, invalidating your buffers of the MMU, etc. And they are megabytes of data is just wasted. Okay, they have to populate it again. So it takes lots of time to populate them back. So context switching or interappending is expensive. We should avoid it as much as possible. Okay, good. So logically, okay, things are like this. Of course, this is not a physical picture. It's a logical picture. Okay. So there is a controller for all the devices one by one, and the drivers are parts of the operating system. Printer driver, camera driver, CD-ROM driver. They are part of the operating system. Rest of the operating system communicates with these devices through the drivers. Okay. Usually this driver, okay, this driver is provided by the manufacturer of the camera. Camera manufacturer manufactures this camera. Also, they provide some kind of a controller physical device so that you can put them in, install them in your PCI slots in your computer. They also provide a driver too, software part of it too. And you take that software and you make it part of your operating system. Most of the time, these drivers are parts of your operating system. Parts of your operating system. Okay? And Microsoft or other operating system manufacturers, they say that if there is an operating system crash, it is usually the fault of the drivers. Drivers provided by these kind of manufacturers. They say that I have to run this driver in my kernel mode, and when they cause an error, it crashes the whole operating system. It causes the whole operating system. It's not my fault. And people say that, well, it is mostly your fault because you designed the operating system. You designed it you designed it to you designed it to be this way. It was your decision to make these drivers part of the operating system, etc. But this is the picture for most of the operating systems. Okay. So the device drivers are part of the operating system, and they come with the devices that you install. Nowadays, most of those device drivers are standardized because most of these kind of devices are using the USB interfaces. And the USB device drivers are already there for most of the devices. So whenever I install a new device to my computer, the device driver is already there because it is using a standard USB device. Okay. Let's talk about those. So a major source of system crashes is buggy drivers. So to prevent this, to prevent the drivers becoming part of the operating system, some operating systems say that I am going to keep the device drivers outside of my kernel. Okay, so this operating system, Minix 3, or those kind of operating system, which we call them the microkernels, microkernel operating systems. Those microkernel operating systems, they say that I am going to keep my operating system minimal, the kernel operating system minimal, very, very small. I will keep even the device drivers out of my kernel. But then how are they going to access the camcorder special registers or the printer special registers? but they will have to make system calls, right? If you take this device driver, printer driver, to the user space, printer driver to the user space, to be able to access the controller's special registers, they have to make system calls. Well, system call means it's a context switch. Context switch means it is expensive. So these kind of microkernel operating systems, they make a trade-off, okay? They are safer, they are more robust against the crashes, but they are less efficient, they are slower because they cause lots of context switches. They make lots of system calls, okay? So that is the downside of it. But sometimes they find ways of cheaper system calls, making special system calls cheaper, but that doesn't make them as efficient as these kind of systems. The most efficient operating system is the operating system that lets everybody do whatever they want, okay? They let the end users do whatever they want. They can access anywhere they like. This is the most efficient because there is no context switch there, right? But we know that this is not manageable. This is not manageable. It has lots of security problems. It has lots of um, manageability, fairness, and robustness problems. Okay, so we don't do it this way. So most of the time we do this trade-off. Trade-off efficiency, trade-off between the efficiency and the robustness, efficiency and the security, efficiency and system modularity, etc. Okay, we talked about those. Okay, so most operating systems, they define standard interfaces, and they say that I have two types of devices. One is a blocked device, one is a character device. Block devices, they read and write data by the blocks, read this many bytes and write this many bytes. And there are character devices, you read your data byte by byte, for example, keyboard and mouse. So as an end user, if you know the difference, then you are fine. You don't have to know about where your data is, stored and etc. Okay, good. So trying to isolate the user from the details of the devices is something that we like all the time. That's why we like this device independent I/O software. In these issues, okay, in this buffering or error reporting or uniform interfacing, of course, we like our I/O software to be device independent. Okay, so let's look at them maybe one by one a little bit. Of course, I don't want to deal with this kind of a picture. Okay, for every type of disk technology, for example, this USB disk technology. This is an old disk drive technology, SCSI disk. SATA is already there. Okay, each one has a different type of interface. Of course, I like my interface to be the same. So this will make my operating system a lot simpler. I don't have to know the difference between those. Okay, so this is what we mean by uniform interfacing. And so this is going to make my operating system a lot simpler, cheaper, more efficient. But of course, each of them will be more complicated now because they will have to convert everything to this standard interface. Okay. So I don't want to talk about this iNumber thing, which is about Unix and everything. No, I will skip this one. Buffering is another I/O related software issue, and we like interfacing in this case. Remember I said we need buffers, okay? This is the picture most efficient in terms of memory usage. I am getting some bytes from the network. This is my network device, byte by byte. So I am getting the data from the network, and I store all of my data in the user space. Okay, doesn't use any buffers. This one uses buffers in user space. This one keeps two buffers, one in the kernel space, one in the user space. This one uses buffers more than one in the kernel space, and there is one in the user space. Okay, this one is the most primitive one. It causes lots of problems. Why? Because I have to handle this as from the user side, get the data from the modem and put it in the user space, in the required space, one by one. Not good. We can say that why don't we keep my data in a buffer space in the user space, buffered position in the user space, and that will solve lots of problems. But remember the paging problem. Paging problem is both valid for both of them. If my page that contains this data is out of the memory, if my process is out of the memory, then these two will run into problems. This solves that problem. Okay, always communicate with your devices using the buffers of the user's kernel space. Whenever it is done, then copy it to your user space. Okay, but the main problem with this issue is, okay, while I am copying this data from this location to this location, if new data comes, what am I going to do? Am I going to disregard that data? No. You keep multiple buffers. While you are copying from this location to this location, this modem can copy its data to this new buffer. So it's called double buffering. Okay, double buffering. So that means what? That means I have copies of the same thing in three places, 1, 2, 3 places. Okay, so to provide more efficiency and more robustness, again, I am trading the robustness and efficiency with memory space. Use more memory space to gain more CPU efficiency or the system robustness, system security maybe. Okay, so buffering is used in many places. Some people say that don't use double buffers, but use circular buffers. What's a circular buffer? It is like this. This is my buffer, right? This is in and this is out. Okay, so both of them, they move upwards. Out can move here and in can move here. If out is way up there and cannot move up, then you move out there, okay? So now let me show you the other way. If this is my in and this is my out, this part is the occupied part. If out is moved up here, if out is moved up here, my occupied part becomes like this. But if I cannot move out even more, then out will be here, and this will be my occupied part. This is called circular buffering. Okay, sometimes this is possible. Instead of using double buffering, this is more efficient way of keeping your data. From one side, I am entering the data. From the other side, I am getting it out. Okay. Good. So we will, as you see, I mean, the idea of buffering is so nice, but let's look at this networking picture. This is my, okay, computer 1. This is my computer 2. They are connected over a network. And I
Can
like
I
to
ask a
send,
question before?
and I like to send this data from this location to this location. And to do that, I need to buffer this into my kernel, and then from my kernel to the network controller. And network controller in my network, it keeps copies of it on the network, then do the same thing. And so what I'm saying is I am keeping 1, 2, 3, 4, 5, 6, 7 copies of the same thing over the whole network. So buffering is something that makes things robust, efficient, but in terms of memory usage, buffers are wasting lots of memory. Okay, somebody had a question. What was the question?
It was me.
Yes.
I was going to ask why paging causes a problem. We, I mean, we don't have to throw the pages. We can store them in our disk or somewhere else and retrieve the data when necessary.
If this page is in the memory, this page, yeah, you are right. I mean, I can write my data to this page. But remember, this process is blocked because it is waiting for some data. Since it is blocked, okay, this page is not used by the CPU. So most probably it will be paged out because it is not being used. Since this part is busy, when I page it out, I cannot move, I cannot copy my data there. So it's going to create either inefficiency in terms of paging, or it will cause some data loss. Okay, you are saying that I can pin this page so that it cannot be moved out. But that's again that's against the principles of paging. If a page is not used by the CPU, page it out. So instead of keeping this whole page in my memory, okay, let this page to be paged out. Let's write our data to the special buffer in my kernel space. Okay, that buffer is already there. It's already reserved because to communicate with the modem, the device driver keeps its buffer in the kernel space anyways. Okay. Abdullah, did I answer you right?
In C, couldn't the user space still be paged?
Well, in when you are writing a C program, you are not allowed to talk about the pages, right?
Yes.
I mean, as an end user, you don't care about the paging. In fact, you can't care about the paging because it is all handled by the operating system with the help of the hardware. If you are saying that there must be ways of keeping this page in the memory, yeah, there is. Operating system can mark that page as that, don't switch this out. But again, it is more efficient to page this out and keep my buffer in the kernel space. Okay. I am out of time right now, but I was going to. Okay, how many people are here?
Sir, may I ask something?
So 77 people are here. I have another meeting. I cannot give you the quiz today. Tomorrow I will give you the quiz. I will pick 5 people, okay, at the end of the lecture, and I will ask them a few questions, verbal questions, and give them grades. So I am not going to pick those people from the 77 people, you know. I am going to pick those people from my class list out of 150 people. Somebody was asking a question?
Yes, I was asking about the buffering. Are those two buffer has exactly the same content or they may be differ?
Well, I mean, when I am copying from this location to this location, of course, they are different. First, I copy from modem's internal space to this kernel. Then after I am done, I copy from this position to this position. They are not exact copies of each other all the time. Okay, but when I fill in this buffer, of course, this is different. After I fill in this buffer, after I am done with filling in this buffer, then I copy everything from this location to this location. Okay, and this one will be discarded.
Okay, thank you.
Okay, but I have to keep these buffers. I mean, even though they are not filled in, they have to be in my memory. Okay, that's it for today. Tomorrow we will continue from this position. I'll see you tomorrow.
See you. Thank you, sir.
Yes, sir. Thank you.